you want to see. Prove the.
That's nice. That's nice. So this is not specific to GK. Like it's RISC-V. Anybody using RISC-V will benefit
That's
from this.
Oh, is this in EVM-SM?
Yes.
Nice. Okay, I think we're happy to start again. So this session is about front ends, that is circuits. And so the first talk we'll have is by James on zkLean, and I'll let you.
All right. Thank you, Alex. Yeah, so this is a talk on zkLean, which is a DSL in lean for writing zk statements and verifying those statements. This is joint work with some of my former colleagues at Galois, as well as Lisa and Carl. So why do we want zkLean? I don't think I need to convince everyone here why zk is great. It's being deployed in all these amazing applications like blockchain, anonymous credentials, voting systems, and post-quantum signatures. These systems are being used to protect billions of dollars in assets, so we want to make sure that they're actually secure and not vulnerable to being stolen. So as most of us probably know, writing zk statements can be complex and difficult to write. So if you have a single bug, single soundness bug in your implementation, this can render your whole proof system basically worthless, and you can prove false or anything like that. So the solution we're proposing here is to use zkLean. And you could use zkLean to verify that your front-end zk statement is correct with respect to some specification, and you can use this to verify soundness of your system. So just as an overview of what zkLean is, so it's a DSL that's implemented in a library for Lean, and it's a way to easily write zk statements. It allows you to, it supports most zk features, so for instance, R1CS, higher degree constraints, lookup tables, MLE-based lookup tables, and we even support RAM if your backend supports that. There are two primary ways that you would typically use zkLean. One is, let's say you have your arithmetization in some other language like Rust. You could say have some tool that extracts that arithmetization, converts it into zkLean, and then once it's in Lean, you're able to verify that it's correct and that kind of thing. The second approach that hasn't happened too much yet, but hopefully this is the approach that happens in the future, is where you can write your statement in zkLean itself. You can verify it correct, and then maybe you pass it to some backend, maybe through LZK or something like that, to verify that your zk statement run in Lean. You can run it in your actual system, and you know that it's correct. zkLean itself is it's agnostic to the backend. We don't really care what proof system you use. And then proofs in Lean can be a bit tedious to do, depending on what you're proving. So we've implemented some tools to help automate this process. And there's the link to the repo if you want to check it out. And I think we'll be updating this to the Ethereum one as well.
Oh, it's already there.
Is it public yet? Oh, well, it's also there. Okay, so here's a really basic example, right? Let's say you want to witness a new variable, and you want it to be constrained to be 0 or 1. So here we have this monadic language. You can see it's a zk builder. That's the monad it lives in. And here we're returning a zk expression, so a zk variable. This is polymorphic over the field. So f is our field here. And the first thing we're doing is we're just calling witness. So this gives you a new witness value. We constrain it to be equal to 0 or 1. So this is a constraint 0 equals x times x minus 1. So traditional way to do this in zk. And then you return this new witness value that you can use in your larger computation. So under the hood, zk Builder, it's a free monad implementation. We found this to be very convenient to express your semantics. But you could also do things like pretty print your circuit if you wanted to extract it into another system. The language provides many different combinators. So you can see how we use witness and constraint eq. And then there's also combinators for doing lookups, lookups with MLEs, reading from RAM and writing from RAM. So in zkLean, we define a operational semantics for circuits. These semantics are executable. So here's like the type definition of the function of what the semantics are. So it takes as input the circuit that you want to run, and then it takes a list of witness values. And then basically it evaluates the circuit and then says, whether or not the circuit is satisfied. So this can be pretty convenient if you want to test out your circuit on different witness values and see if it's correct or not. So here you can see like different runs on different inputs to the witness 0, 1 circuit that we just saw. So if you pass 0 and 1, it returns true. And if you give it some random value other than that, it's going to return false. So the main purpose of zkLean is to do verification of circuits. So this is how you could do soundness of your circuit. So basically soundness is saying that the circuit satisfiability is implying some specification for your circuit, right? The way that you write this in zkLean is it's stated here in this formal proposition. But here we're using Lean's standard do notation. So this allows you to write composable proofs using this like do notation. And this is in like a Hoare triple style. So the way that this works is that let's say on the first brackets, these are like all the preconditions that are given to the circuit. Now we have your like monadic circuit evaluation. And then here you have some specification on the output, so you can make sure that certain conditions and stuff hold over your circuit. And the nice thing about this is that it allows you to compose many different lemmas and statements together. So if you have a subcomponent of a circuit, you could easily write your circuit function over that. And then you can build up higher level proofs by composing all these calls using these Hoare triples and some built-in machinery that Lean provides. So let's look at a case study that we did. So we proved a circuit for Ketchak. So the first thing you need when you want to prove a circuit correct is you need a reference specification. So this is an excerpt of what Ketchak's implementation looks like in Lean. Here's the state of Ketchak, and here you can see you have 25 lanes. And notice that these are all over 64-bit bit vectors. And now you have your round function, where it's calling helper functions for theta, rho, and all the parts of Ketchak round. And then now for your overall Ketchak, you're just doing a fold over that Ketchak round, so you're doing 24 evaluations of that. So now if you want to implement this in zkLean, it's actually, I think it's pretty nice and very close to the actual specification itself. So here we're defining a state again, and again with our 25 lanes. But in this case, we have a zk expression over some field. So notice before, the specification was over a bit vector. And now we're just changing to whatever field you're using. Yeah, and again, if you look, we define the circuit for a Ketchak round in this case. So again, we're calling theta, rho, pi, et cetera. Except now we live in this zk builder monad to build our circuit. And then you do monadic bind to pipe along the state between all these subfunctions. And then again, you can just do a fold over like the 24 rounds, and then this builds up the whole Ketchak circuit, and it's pretty nice and modular. Okay, so now that we've defined all that, we want to prove correctness, soundness of our Ketchak round circuit. So this is the soundness statement. You can see that, so it's taking, it's reasoning about two states, the state over your field elements that are used in your circuit, and then also the reference specification state. And again, as a reminder, these are over the bit vectors. So as a precondition here, you have a an equivalence between the bit vector representation and the field element representation. So the two inputs have to be the same. And then in the post condition here, you're saying that an evaluation of the spec of a round of Ketchak, so this is over the bit vector representation, that's equivalent to the output of the circuit evaluation. So this is sort of doing a simulation proof over the reference semantics and the circuit. And you can see, since we're integrating with Lean standard do notation, this is like very nice and composable. So if you're not too familiar with Lean, you're introducing a few variables. You're doing a few simple rewrites based on unfolding the Ketchak definitions that we've defined. And then here we're just doing a few spec calls to all the subcomponent lemmas. So there's one lemma for theta soundness, one lemma for rho soundness, chi soundness, etc. And then here you end up with like a pretty nice, simple composable proof of a Ketchak round. Obviously, anytime you're doing formal methods, it's important to be explicit about what your trusted computing base is. So here in ZKLean, you're basically trusting the operational semantics that I told you about earlier. It's pretty small, so you can inspect it yourself, but you're still trusting that that's implemented correctly. You also need to trust your extraction either to or from Lean. So you want to make sure that you're verifying the thing that you're actually running in production. You're also trusting that the specification that you've written is correct. And then, obviously, the Lean kernel. I guess Julian over lunch was saying they just found one soundness bug in the kernel, so you can ask him about it later. I think there's some overflow, and you could basically overwrite all memory.
That's in the runtime execution, it's not in the kernel.
Okay, so maybe it's fine.
Yeah, if you run a program, you can hit a bug, but it doesn't affect proofs.
Okay, well, it's good to know. Okay, so like I mentioned, there's like a few ways you could integrate with zkLean. So one thing you can do is you could write a custom extraction from your, say, your like Rust backend or whatever. So we've done this for Jolt. So we wrote a custom extractor from Jolt into zkLean. This is basically like a binary tool that links against Jolt's library. It extracts all the MLE tables for all of the instructions in their lookups. And then now we have basically Lean representations of all of Jolt's front-end semantics. So here's like an example of what this looks like when you run this extraction tool. So on the top, this is the lasso lookup table for equality. So this is like the RISC-V equality instruction. So like that's what the Jolt Rust code looks like at the top. It's basically taking its list of inputs, points, and evaluating the polynomial. When you run it through our extractor, you get this expression at the bottom, which basically works by linking against this function, building up an AST representation of the function, and then it just pretty prints the output. So you have pretty high confidence that the expression that you end up with in Lean is actually corresponding to what you're running on the Rust side. So while you can write custom extractors, they are like pretty intensive, and you have to do it for each system. So an alternative integration approach that we've taken is to integrate with LLZK. So this is, I don't know if any of the Veradice guys are here, but this is a system developed by Veradice, and it's like a MLIR dialect for ZK. So the advantage of this is it kind of solves like the LLVM problem of like having a bunch of front ends and a bunch of back ends. So similarly here, like if you have a bunch of front ends like Circom or SP1, and then you have a bunch of back ends, it solves the n squared problem or whatever. So what we've done is we've actually implemented front ends and back ends for zkLean. So let's say you were to write your front end statement in zkLean, you compile it to LZK, and then you could use LZK to compile it to whatever backend that you care about, like I don't know what's currently supported, but maybe like R1CS or, yeah. But eventually probably air and the,
So front ends we have Airbender now as well.
okay,
And
yeah,
I guess Martin over there is working on more.
cool, yep.
And backends, I guess there's a Python backend now as well, or SMT backend in general.
Yep. And yeah, so, and then we've also implemented the zkLean backend. So like, if you have your SP1 circuit, you could run it through LZK, and then you'll get a zkLean representation of your circuit. So this is a much more modular way to get usage in zkLean. So just as another simple example, this is like, a very simple is0 circuit in Circom. And then on the right-hand side, this is like what the LZK output in zkLean looks like. I mean, here, these are the two main constraints that you care about, right? You want to make sure that the negative input times the inverse plus 1, that output equals, times the input equals 0. So you can see it's a little more laid out since it's automatically generated, and this is also a bit simplified. But here you can see the input, negative input, times the inverse, plus 1. You're constraining that equal to the output variable. And then you're also constraining that the input times the output is equal to 0. So it's pretty one-to-one mapping, and you can like follow it and make sure that it matches what you expect. Yeah, so like I mentioned earlier, we've implemented some automation to help with the ergonomics of doing proofs over belt circuits. So this work was actually just accepted to CAV, so Lisa will be presenting that later this summer. But basically, we've implemented a tactic in Lean called bitmod EQ, and this helps you automate some of these proofs between like field arithmetic and bit vectors. So yeah, helping you solve those kinds of problems if you're proving those about your circuits. So let's start with an example. This is Jolt's encoding of bitwise OR. Just to see like why this works, let's look at like 1 bit. So let's say, 1 plus 1 minus 1 is 1. 1 plus All right, I won't go through the rest of these, but you can see that the truth table actually represents bitwise OR. And yeah, so our goal here is to prove that actually, when you represent it, the finite field math of that actually represents the bitwise OR operation. So here you can see we have preconditions at the top that each of the bits of xi correspond to bit vector 1, and all the bits of y correspond to bit vector 2. And then here our postcondition, or our goal is that the bitwise XOR of BV1 and BV2 are equivalent to the field arithmetic of that MLE expression I just showed. So the way that bitmod EQ works is that initially we have some statement over both finite fields and bit vectors. We do some range analysis to basically convert all these into statements over natural numbers and bit vectors. Again, we do more range analysis to convert all the natural numbers into bit vectors itself. And then once everything's in bit vector land, this is very nice for like existing automatic solving tools. So we use like BV_decide to automatically bit blast, and then this will be able to automatically verify the statement for us. These are the rules that we use to do all these range analyses. The ones on the left are from the finite fields to natural numbers, and then on the right are from natural numbers to bit vectors. These are a bunch of range analyses. I don't know, maybe to highlight one, like if you look at disnat here, if you have 2 nat of an addition, you can split it up into 2 nat of the left plus 2 nat of the right, given up, and if you add a modulus over the field. So, yep. So to evaluate the system, we did 2 real-world case studies. The first was the Jolt ZKVM, and then we also evaluated it on Cersei. So for Jolt, we verified all of the lasso lookup tables and all the 32-bit twist and shout lookup tables. And these, again, are encoding all the RISC-V instructions. And then for Cersei, Cersei is basically like a verified compiler for ZK. Previously, it only had like an SMT backend, and we've basically added a like lean verification backend for Cersei. So here you can like kind of look at like what we're able to solve versus the existing SMT solutions. So initially, like we do have a little bit higher overhead in terms of runtime on like the smaller instances, but then the SMT solver like caps out and isn't able to like solve all the problems. But you can see like with Bitmod EQ, we're able to solve all the jolt problems, even if it takes a little longer, but it's like trivially longer on the small cases. And then same thing for Cersei, we're able to solve much more of the Cersei cases. So. And yeah, if you're just comparing Bitmod EQ versus like manual effort of doing all these proofs, so Lisa did like one of these proofs manually by herself, and it was like, I guess 200 lines, and it took her 10 hours or something like that. And yeah, now on the right-hand side, I guess now it's 5 lines and it takes 10 seconds to run. I think you could get this down to 2 lines pretty easily. And then you can see like the savings, right? Like over 32 lookup tables. You know, that's how many lines of code you would save, and like that's how much effort you would save in terms of developer time. So I think pretty nice results. So yeah, in summary, we've been developing zkLean, which allows you to write zk statements in Lean in a pretty nice and composable manner. It gives you a way to do compositional proofs, integrating with like existing Lean infrastructure around like standard do. We have this integration with ZK, so you can easily integrate zkLean with your existing proof systems, and hopefully more will be added as the LZK infrastructure continues to evolve and grow. And then we've implemented Bitmod EQ, which is this tactic to help you with these proofs and automate them. So yeah, I encourage you to give it a try, and yeah, let us know what you think.
All right, we have time for some questions. I guess, Mark, are you switching out? Yeah. Any questions?
Thanks for the talk. Really interesting work, especially with the tactic. How does zkLean relate to clean?
I think it's a similar space. I think maybe there's a few design differences around how like statements are represented in Lean. Oh yeah, we don't support explicit witness generation. Although basically, since you could just write a Lean function that does witness generation, and then that like basically covers it. But we don't have like explicit like support in the language for witness generation. We don't have a separate notion between like subcircuits and circuits. So I do think that's nice, like in terms of the composability of using like standard do for these like core triples. Oh, there are no more subcircuits?
Still is. I'll be lazy about this.
So maybe eventually they will be similar, more similar. So yeah.
And then, do you use it for formal verification, like to extract constraints and specify and verify?
Yeah. So all those like Jolt ones, like those are extracted from Jolt's code base, and they're verified.
Cool.
So it's in the actual Jolt repository.
Yeah.
Oh,
That
very
extraction
cool.
code is in Jolt's source code, and I mean the goal eventually would be to like run in CI like extraction every time they make a PR, and then like in CI verify that the proofs still pass or whatever.
100%, yeah.
Yeah.
Cool.
Why not do that now?
So they switched to 64 bits, and Lean can actually type check the 64-bit, some of the larger 64-bit polynomials just because of the size. So it would require more engineering effort to just fix that basically. So.
Any other questions?